Hi everyone, I'm Hyunkook Lee from the APL of the University of Huddersfield. This is part 2 of my listening test design tutorial. You can also watch part 1 grading test from our YouTube channel. The main aim of a psychophysical test is to estimate a perceptual threshold or sensitivity in detecting a signal or discriminating between signals with different intensities. As this diagram illustrates, there are basically two internal processes when we hear an auditory stimulus. Firstly, the sensory process transforms the input signal, the physical stimulus, into internal sensation. And the decision process makes a decision on our response to the stimulus based on the sensory process. So the task in psychophysical test is basically to measure the response resulting from these two internal processes. But there are two different models of signal detection. One is threshold theory and the other is signal detection theory. And each model requires a different test design. Firstly, the threshold theory assumes that the sensory process has a perceptual threshold, and this threshold is defined as a minimum stimulus intensity above which the sensory process leads to a correct decision. So only above the threshold a signal can be correctly detected. It could be either absolute threshold like absolute hearing threshold of a single tone, or just noticeable difference between a reference and a signal with various levels. And the analysis based on the threshold theory relies on a psychometric function estimated from the percent correct of responses from the subject. On the other hand, the signal detection theory does not support the existence of absolute threshold. It assumes the absolute threshold does not exist because there is always a bias involved in decision-making process due to the existence of noise condition. For example, the state of mind or any external environmental conditions can influence our decision process, and therefore the response can vary time to time, even for the same stimulus. So SDT analysis measures sensitivity and decision criterion instead of threshold, although threshold can be estimated as well from an SDT experiment. Test procedures or method used for psychophysical tests can be broadly classified as classical methods and adaptive methods. The classical methods were developed by Fechner in 1860. There are basically three methods: method of constant stimuli, method of limits, and method of adjustment. These methods are generally quite time consuming and also prone to psychological errors like habituation and expectation errors, especially for method of limits and method of adjustment. Just to briefly introduce these three methods, the method of constant stimuli present stimuli with different intensities repeatedly at random and obtain a psychometric function based on the percent correct of responses obtained for each stimulus intensity. And from this, a threshold is estimated. The method of limit measures a threshold by running multiple tests that present the stimuli in either ascending or descending order of intensity. So this test does not require a psychometric function to estimate the threshold, but it asks the subject to find the threshold at each sitting with multiple trials presented in ascending or descending orders. And so it's less time consuming than the method of constant, but could be prone to the habituation and expectation errors. With the method of adjustment, the subject himself or herself controls the stimulus intensity to find the threshold. So this method could be faster than the other two methods, but psychological errors like habituation error still exist, especially the subject might easily pass the actual threshold point due to the habit of changing the intensity. On the other hand, with the adaptive methods, the stimulus level in the following trial is determined adaptively based on the response for the current trial or the statistics of the previous trials. So this is a more efficient method for estimating a threshold compared to the method of constant stimuli. Probably the most popular adaptive method used in psychophysical tests are end-down one-up staircase method or PAST. Later on, we'll look at a few examples of the end-down one-up staircase method. For a given test procedure, different types of tasks can be chosen to elicit the subject's response. For example, yes-no task is typically used to estimate an absolute threshold, where the subject is asked whether they heard the signal or not. The 2AFC, two alternative force choice method, is also a popular method used for estimating just noticeable difference in auditory psychophysical experiments. There are spatial and temporal 2AFC tasks. The spatial 2AFC is relevant for visual test, for example, where the subject is presented with one visual object on the left-hand side and the other on the right-hand side, and they are asked to choose which one has a higher intensity, for example. But in the context of auditory test, it is always temporal 2AFC because two stimuli are presented one by one with a short time gap in between. That's why it is often called two-interval first choice method or two-interval 2AFC. And ABX is a very popular method used in auditory test that examines a detectability of difference between stimuli. And it is actually a type of a 2AFC method with three stimuli. So it's often called three-interval 2AFC. And we'll look into the ABX task further later on. So now let's consider some practical psychophysical testing scenario. In this example, we want to estimate the absolute hearing threshold for a tone. And we use the method of constant stimuli with yes-no task here. And let's say the stimuli are 100 Hz tones with varied SPLs of 10 dB, 15, 20, 25, and 30 dB. And we present the subject with these stimuli many times, say at least 20 times to obtain a reasonable percent correct for each SPL. So in this example, we have a total of 100 trials, 5 stimuli level times 20 repetitions for each subject to complete in a session. And it's important that the stimuli are presented in a randomized order, and the subject is asked a question like, did it play the tone? And they respond by either saying yes or no. Because the tone is always present in this type of test, in the method of constant stimuli, there is always signal present in each trial. So then yes is always the positive answer and no is always the negative answer. And from the data collected, we calculate percent positive responses for each intensity level. And using a statistical method such as maximum likelihood estimation, we can derive a psychometric function fitting the obtained perceived positive responses. And for a yes-no task, a threshold is estimated to be the lowest stimulus intensity that can be detected at 50% positive responses on the psychometric function. But this kind of classical method based on the threshold theory has been claimed to have some limitations. Again, in the method of constant stimuli, a signal is always present in each trial, so the possible outcomes are only hit or miss. If the response is yes, then it's hit, and if it's no, then it's miss. So because the threshold model uses only percent correct, which is the hit rate, we don't know whether the result has been influenced by an internal bias or not. So the signal detection theory, in short we call it SDT, was proposed as an alternative analysis framework to the psychometric threshold model in the 1950s. SDT assumes that a perfect threshold does not exist due to potential bias. In other words, the ability to correctly detect the signal is influenced by the presence of uncertainty, which we can refer to as noise. So instead of measuring threshold, SDT measures discriminability factor, which is sensitivity, and we call it D prime, and bias factor, which is the decision criterion, rather than measuring the threshold. So the D prime and C decision criterion are calculated from the hit and false alarm rates. And now let's have a look at this a table where we can explain what's hit, what's false alarm, and so on. So with the yes-no task, let's say the stimulus presented included the signal as well as noise. And the subject response was yes. Then it's hit, obviously. But if the response was no, then it's miss. On the other hand, if the presented stimulus in the trial was a noise, so or maybe just a silence, but then the subject response was yes, then we call it false alarm. So for example, when there was only a silence and the question was there a tone presented? And if the response was yes, then it would be false alarm. But when the report was no, then it would be a correct rejection. So what do we mean by sensitivity and bias? Sensitivity is basically the distance between the peaks of the probability density functions for signal and noise. Each probability density function represents the probability of our internal response as to whether the stimulus is a signal or noise. For example, when we hear a very quiet tone, we might think it's a tone, but we may also think it's a silence, perhaps influenced by some noise present in the background, which would influence our decision process. So when there is no bias towards after either noise or signal, then this is an ideal case where we can make a neutral decision because the decision criterion C lies exactly in between the two peaks of the probability density functions of our internal response. But when a bias occurs due to the state of mind, physical condition, mood, past experience or expectation, etc., the decision criteria can move to either left or right. So for example, if C moves to the left, this means that the decision the subject makes becomes more liberal because the subject is basically to say yes more often, then the hit rate will increase naturally and the miss rate will be decreased. But at the same time, the false alarm rate will also increase. In this case, even if the sensitivity is still the same, the result has a bias. It's basically influenced by the bias. So we can say it's not very reliable. If the criteria moves to the right, then this means we make more conservative decision because there will be more negative responses. There will be an increased correct rejection rate, but this also increases the rate of for miss. So in an ideal scenario, we should always have this criterion lie in between the signal and noise. So this means that our decision process is not influenced by bias. And obviously, when the difference between two stimuli is large, then the sensitivity will increase. The peaks between the 2 points will become larger, whilst the criterion still lies in the middle. Then we can say that we can definitely here detect the difference between the stimuli and decision made was not influenced by bias. So let's take a practical example. When designing an SDT experiment, it's important to remember that we need to include noise trials as well as signal trials. In the method of constant stimuli test, we only had signal trials presented in a random order. But to allow for SDT analysis, for each stimulus intensity, we must have the same number of signal and noise trials presented repeatedly in a randomized order. So in this example of yes-no tone detection task, in session 1, we present the 20 dB tone stimulus 20 times, but also we include 20 silent trials, and they are intermixed within this session. And after finishing this session, we move on to the second session. Then we test another stimulus selected at random. And then we go through the same process and again and again. And then eventually we calculate the sensitivity and bias for each stimulus intensity. Then from the responses collected, we can calculate the hit and false alarm rates. If the stimulus was a tone and the response was yes, then it's hit. But if the stimulus was silence and the subject still says yes, then it's false alarm. Now the sensitivity can be calculated by subtracting the z-score of false alarm rate from the z-score of the hit rate. And we can also calculate the decision criterion C by this simple equation here. Although the main aim of a traditional SDT analysis is to obtain the sensitivity and bias, we can also calculate percent correct from the responses we collected. From this, a psychometric function can also be derived. And if you want to learn more details about its signal detection model and sensitivity and criterion calculations, Macmillan and Krillman's book, Detection Theory, a User Guide, is a very good reference. Let's also consider an example of 2IFC or temporal 2AFC test conducted in an SDT framework. Let's say we are measuring the J and D, just noticeable difference of perceived loudness. And we have multiple stimuli with different SPLs to test. And these stimuli are called comparison stimuli. Then in each session, each of these comparison stimuli is paired with a standard stimulus, in this case a stimulus with 50 dB SPL. This is basically a reference stimulus with the level staying constant in each trial. But the important thing to remember here is that the presentation order of the standard and comparison stimuli in each pair should be randomized, such that the number of SC trials and the number of CS trials should be the same. So in one trial, the comparison is presented first, and then the standard after a certain time gap. But in the second trial, the standard stimulus is presented first, and then the comparison stimulus follows, and so on. But the important thing is that the number of SC trials and CS trials should be the same. In this example, we have 20 times each. Then the subject is forced to choose the loudest stimulus between A and B, which is why it's called a forced choice task. And after finishing the session, then we move on to the next session with the randomly selected stimulus intensity. Now let's talk about how we should interpret the responses from the 2IFC experiment. Since a comparison stimulus is always supposed to be louder than the standard stimulus, we can say it's hit if the subject answers A when A is comparison and B is standard. But when A is standard and B is comparison, and the subject reports A, then we can consider it as a false alarm because standard is a lower SPL than comparison, but standard is still responded to be a louder stimulus, then it's a false alarm. In fact, in a 2AFC task, there are only hit and false alarm we need to consider. If you look at the case where the subject response is B, we can still think of two cases, hit and false alarm. For example, if B is standard and this subject says B is louder, then this case is false alarm as well. But then if B is comparison and the subject response was B, then it's hit because comparison is louder than standard. Then we calculate sensitivity and bias. We only need one set of hit and false alarm responses from either the response A or the response B, because the result is essentially identical either way. Now let's talk a bit about ABX test, which is a very popular type of test in audio engineering, but often conducted in an incorrect way from the signal detection theory point of view. So it's usually conducted such a way that the subject can switch between A, B, and X freely and listen to them repeatedly until they find their answer. But this actually violates the typical presentation rules of psychophysical method, which involves a set number of repeated trials of single stimulus or paired stimuli to obtain a psychometric function of percent correct or sensitivity. So, allowing unlimited self-switching and repeat within a trial might cause more confusion and bias, because the decision criterion might be moved to the left or right constantly, and the listener might eventually get more confused, and also there would be listening fatigue if they try to compare the A, B, and X repeatedly, and eventually the whole test might take longer. So the correct way of conducting an ABX test would be that in each trial, A, B, and X is presented just once with an interstimulus interval of around 300 milliseconds. And the same conditions should be repeated many times, I would say at least 20 times, to allow some reliable statistics, with X randomized between A and B. So the presentation order of A and B are fixed. So A could be the standard, B is the comparison, and X could be either A or B, randomized in each session. To allow for an SDT analysis, the number of the trials with X equals A and X equals B should be the same. Then we can calculate D prime and C from the hit and false alarm rates in a similar way that we saw in the 2IFC example. Lastly, I'd like to briefly discuss adaptive staircase methods. The method of constant stimuli or non-adaptive test can be quite time-consuming because all intensities need to be tested repeatedly, equal number of times, to derive a psychometric function from which you can estimate a threshold. But if you're only interested in estimating the threshold, this can be a quite inefficient method. On the other hand, adaptive staircase up-down methods are designed to estimate a threshold in a more efficient way. So they determine the stimulus intensity of the next trial adaptively according to the response from the current trial. So it's a more time-efficient method than method of constant stimuli or other non-adaptive methods. And various tasks like Yes-No, 2AFC, or ABX can be used in each trial for the staircase procedure. Okay, so let's take a practical example. The basic rule of adaptive staircase one-down, one-up method is that if the response in the current trial is positive, then the stimulus intensity or difference is one step decreased in the next trial, which means the task becomes more difficult. If the answer is negative, then the level is one step increased in the next trial, which means the task becomes easier. So let's have a look at this example. Let's say we are doing yes-no task experiment, and we start with stimulus intensity, which is fairly high. So let's take a look at this example of a yes-no experiment. The first trial usually starts with a stimulus with the highest intensity. So in this case, we have this stimulus with 12 dB level. And if you heard the signal, if the response was yes, then in the next trial, the level is decreased by 1 steps. So in our case, 2 dB is decreased. And if the response is still yes, then we decrease the level by another step. So now it becomes 8 dB. So basically what we're doing here is, as the trial number increases, we are decreasing the intensity level, which means the test becomes more difficult. So we repeat this until it reaches the first reversal point. Now finally at 4 dB condition, we cannot hear the signal, so the response is no. Then we make the test a little bit easier. So we go back to the 6 dB condition. Now ask the same question. If the response is still no, then we increase the step by another 2 dB. And now if the response is yes, then we decrease the level by 2 dB again. And if the response in the current trial is no, then we go back up to 8 dB. So we continue this process until we reach about 50 to 60 trials in total, or if we obtain 6 to 12 reversal points, then the test is terminated. And the threshold is estimated by averaging the levels at the last n reversal points. For example, 8 reversal points. We average the intensities at those reversal points. That is estimated threshold. And the threshold measured from 1 down, 1 up procedure is equivalent to the intensity at 50% probability of a positive responses on a psychometric function. The traditional 1 down, 1 up adaptive staircase method has been modified by Levitt, and these are called transformed staircase methods. Probably the most widely used form of transformed staircase is 2 down, 1 up, which requires 2 consecutive trials with the positive response before decreasing the intensity, and this is applied beyond the first reversal point. Now let's have a look at this example of the same yes-no task. Again, we start with 12 dB condition in the first trial. If the response is yes, then we decrease the level by 2 dB, and we repeat this until we reach the first reversal point. And now, if the answer is no, we increase the level by 2 dB again. And we ask the question, if the response is yes at this point, the important thing is that we repeat the same condition once again and ask the same question. Now, if we get 2 consecutive yes responses, then we decrease the level again. And in this trial, if the response is no, then we increase the level by 2 dB. And if it is still no, then we increase the level by another 2 dB. Now we get this yes response, and again, we have to repeat the same condition once again and see if the response is still yes, and there are 2 yeses in a row, then we can decrease the level in the next trial. And we repeat this process until we reach 50, 60 trials or a certain number of reversal points. And we estimate the threshold by averaging the last couple of reversal points. The threshold measured from the 2 down, 1 up procedure is equivalent to the intensity at the 70.7% probability of positive responses on a psychometric function, as opposed to 50% point with 1 up, 1 down rule. Okay, so lastly, I'd like to quickly introduce HULTI-GEN version 2, which is a Mac-based software tool for generating and customizing listening test interface. HULTI-GEN version 1 was released in 2015, and it's been used for listening tests by many researchers and students around the world. But it was limited to just grading methods like the ITUR or ITUT methods. So here we are announcing HULTI-GEN version 2, which supports psychophysical tests as well as grading tests. And also it provides a significantly improved workflow as well. So the new version includes all of the ITUR, ITUT methods by default, and also provide interface for yes-no, 2AFC, and ABX tasks in both non-adaptive and adaptive staircase procedures. And it also supports the SDT-based test design as well. And version 2 is released as an open source framework, so you can customize existing tests or even add new types of tests yourself. There are also some new features added to HULTI-GEN version 2. It supports multi-channel playback up to 64 channels, so it'd be useful for conducting 3D audio quality evaluation. And it also provides binauralization of the multi-channel signals using SOFA, HRIR, or BRIR data, so you can simulate virtual loudspeaker listening over headphones. And an extensive set of headphone equalization filters are provided, which might be useful when your tests need to be conducted remotely and the subjects use different types of headphones. The session configuration and file management system has also been improved from version 1, so it's now very easy to load different stimulus files and map them to different test sessions or groups. Lastly, version 2 offers a very flexible customization of the GUI design and utilizes config and subject files in the JSON format like version 1, but now it saves the results as CSV, so it's ready-made for statistical analysis. Okay, so that's it for this session. Thank you for listening. Please email me or leave comments if you have any questions. I hope you all keep safe and well, and see you next time.